Hello everyone, we're going to be going over section 6.4 today. So this is on graphs of the sine and cosine functions. So we have 5 objectives. Number 1 being we want to graph the sine function y is equal to sine x and functions of the form of y equals to a sine of, and that is not a w but a omega. So that's the lowercase Greek symbol for omega. So y is equal to a sine of omega x. Graph number 2, graph the cosine function y is equal to cosine x and functions of the form y is equal to a cosine of omega x. 3, determine the amplitude and period of sinusoidal functions. 4, graph sinusoidal functions using key points. And 5, find an equation for a sinusoidal graph. So just to review, here we have our 6 trigonometric functions, and we can go ahead and we can graph each one of these functions in the xy plane if we change their variables to x and y instead of t or theta as we had before. Now we're going to consider them with x and y so that we're able to actually graph them on our xy plane. So we'll see them as y is equal to sine of x, y is equal to cosecant of x, y is equal to cosine of x, y is equal to secant of x, and y is equal to tangent of x, and y is equal to cotangent of x. So this is our new form that we're going to have them in, and corresponds to the angle which is measured in radians. So y would then be the result of the dependent variable, while x is going to correspond to the angle which we are measuring in radians. So we're not measuring in degrees for this section. So objective 1, graph the sine function y is equal to sine of x and functions of the form y is equal to a sine of omega x. So since sine has a period of 2 pi, we really only need to graph the sine function on the interval 0 to 2 pi. Anything other than that, it will just keep repeating whatever formation we saw between 0 and 2 pi. So it goes on forever in each direction. So when we graph it, it's really just important that we focus on one period and just know that it continues on. So when graphing the sine function, it's helpful to only plot the important and or easy points to plot. There's no real point in trying to plot each and every single point that we have on our unit circle, correspond that to an XY graph. We can just focus on trying to graph the ones that are easier or straightforward and connecting those dots. So important points would be things like pi over 2, 1, or pi is 0, etc. Anything that has that max or min value of 1 or negative 1, and any time the function crosses the x-axis or has a value of 0. So those would be our important points. They're also easy points, but they're very important. Easier points that may not be quite as important, but because they're easy, they are easier to graph. Those would be something like pi over 6 and 1/2, or 7 pi over 6 negative 1/2, things like that. So let's go ahead and look at our sine function here. So we see our sine function, we have our graph here between 0 and 2 pi. Our function does continue, so we can always draw lines going this way to signify that this function is continuing on. But either way, we know that we're just focusing between 0 and 2 pi. But so what we see here is that we have the specific curve. We have our function going through the origin. We have this increasing slope here. We have our max value at 1. We come back down, we go through the x-axis, or have a value of 0. And then we go down here to our minimum value, which is negative 1. And then we come up back through the x-axis to give us a value of 0 to continue on with this pattern. So with sine, the important points that we're looking at are going to be 0, pi, 2 pi, and pi halves, and 3 pi halves. So we're looking at our intervals or our integer multiples of pi halves. Those are going to be our important points. And since when we have our integer multiples of pi over 6, so pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6, when we have these integer multiples of pi over 6, we also see that our y value ends up being 1/2 or negative 1/2, so those make it easier to graph as well. So those are some easier points we can include. So all right, this graph is one period or one cycle. of the graph y equals sine of x. So between 0 and 2 pi, that is one period of our graph, which is also called a cycle. So we can continue the graph in both directions, which we talked about, to get a complete graph of y is equal to sine of x. In our book, we're also given a table with all of these values. So in our table, we have all the values that correspond to the angle measurement, what the y value of that is, or the y coordinate on our graph, and then it shows you the actual points. So this is a table with all of the values summarized up. The graph also illustrates specific properties of sine. So with properties of the sine function, the domain is the set of all real numbers. Since we see our sine function continue in the positive and negative direction infinitely, that means that it has a domain of all real numbers. Then the range consists of real numbers from -1 to 1 inclusive. So that just means that it also includes 1 and -1 and any values in between. So we kind of see here, this would end up being our range. So our range is going from -1 to 1, and we're just finding these values in between. The sine function is an odd function, as the symmetry of the graph with respect to the origin indicates. So our function is odd. We also know that it is odd because if we plug in a negative x value, our sine function will then be negative. That's another way that we know it's odd. But we also know it's odd because it is reflected about the origin. Since we see that it is flipped, since on the positive side of the origin, we have this increasing slope, and on the negative side of the origin, we have a decreasing slope. So it's reflected about the origin. So the sine function is periodic with a period of 2 pi, which we went over. The x-intercepts are going to be -2 pi, -pi, 0 pi, 2 pi, 3 pi, and the y-intercept is 0. So there's just that one y-intercept at the origin, and then we see our x-intercepts will be every integer multiple of pi. The maximum value is 1, and it occurs at -3 pi over 2, pi over 2, 5 pi over 2, 9 pi over 2. And the minimum value is -1, which occurs at -pi over 2, 3 pi over 2, 7 pi over 2, 11 pi over 2. So we see those differences there with those integer multiples of pi over 2. Some will have 1, some will be -1. They will be then alternating. So we see that at -pi over 2, we have -1, pi over 2, we have +1. So we see they are alternating in pattern there. So all right, using everything that we went over, for example, when we want to graph y is equal to -3 sine of 2x using transformations, and then we're going to determine the domain and range. Let's zoom out a little bit. So with y is equal to sine of x, we ended up with a graph that looked like this. Now what we're doing is we're multiplying a number by sine of x, and we're multiplying our angle by 2. And what this means is that in y is equal to -3 sine of 2x, the -3 is going to cause the graph of y is equal to sine of x to vertically stretch. So the 3 causes our graph to stretch vertically, so it's going to stretch upwards and downwards because now our minimum and our maximum values will have to be at 3, -3 instead of 1 and -1. That negative in front of the 3 will now reflect. So now we're going to reflect about the x-axis. So we'll go ahead and say the +3. is going to cause the graph of sine of x to vertically stretch. And the negative symbol will make our graph reflect about the x-axis. So we're going to see this flipped. So before we go through the origin, we have this increasing value. We go to 1, we decrease down to -1, we increase again. Instead now, since we're reflecting about the x-axis, we're going to be decreasing down to -3 in this case. Then we're going to go ahead and increase up to +3, and then we'll decrease again. So we're seeing this graph flipped. So that's what happens when we multiply this -3 to the outside of our function. Now the 2 that's multiplying the 2 that's being multiplied by x will cause a horizontal compression by a factor of 1/2. So this means that when we look at our graph here, let's go ahead, we'll use purple. So we look at our graph, our -3 will flip, we'll have this vertical stretch. And now by multiplying our angle by 2, we're going to have a compression. So in our problem, we're stretching we'll go like this to indicate that we need to flip, and then we are compressing. So these are the 3 things we're doing in our problem. We're flipping our graph because it's negative, we're stretching it vertically, and we're compressing it downwards by a factor of 1/2. And this is using our transformation. So the properties of transformation, we know that these are how they affect graphs. So all this to say that our minimum and maximum values are now going to be 3 and -3. Our minimum and maximum values are going to occur now in the same pattern, but everything will be cut in half. So let's write off to the side here because we kind of ran out of room. So now we have min and max values will be at 3 and -3. We see that we're going to have values of 0 or crossing the x-axis. Let's say function will cross x-axis at the half values now. So before we saw that our function crossed the x-axis at 0, pi, and 2 pi. So we're going to cut those in half because we're compressing by a factor of 1/2. So if we're cutting that in half, then that means that our function crosses the x-axis at 0, pi over 2, pi, 3 pi over 2, and so on. So we don't have to actually graph all of these. We just keep them in mind. So now we have these values. These are when our function will cross the x-axis, meaning that we have values of 0. Since we see that our graph is also flipped, we'll get that before, when we had those min and max values, the min and max values occurred at integer multiples of pi over 2. Since we've now compressed by 1/2, this means that our min and max values will now occur at integer multiples of pi over 4. So at pi over 4, we'll have our first minimum value because we're flipping it because of that negative. So we'll have pi over 4, have min value. Then we cross the x-axis at pi halves. So then 3 pi over 4 has max value, which just means that we have the points here of pi over 4, -3, and 3 pi over 4, +3. So all right, let's go ahead and plot these points. So we can label our graph a little bit here. 1, 2, 3, -1, -2, -3. And we'll mark up our graph. So we'll say this is going to be pi over 4. This is pi halves. 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 2 pi, and then this next value should be 7 pi over 2. So we're just going to graph these values. And we'll see very quickly that we're going to end up with a repeating pattern. So we know that our function is still crossing the x-axis at 0. We know that that is happening. Then we know that pi over 4 is going to have the minimum value of -3. So our next point will be right here. Then we're going to cross the x-axis again, pi over 2. Then we have a maximum value at 3 pi over 4, +3. And we cross the x-axis again at pi. So let's connect these dots. Let's go ahead and use blue. And this is going to end up being in the way, so let's move that away. There we go. So now we can connect our dots, thinking about having the same or similar shape as our sine graph. So our shape here is going to look something like this. Come back down, and we connect that point. We see here that a 1 period is now between 0 and pi. This is because we've compressed it by a factor of 1/2, meaning that if our period was 2 pi, we're dividing that by 1/2 into now we see that 1 period is pi. And our graph just continues. We see our graph would continue in that direction as well, but we don't have to continue in that direction. But we can just plot the rest of our points. So our next value, 5 pi over 4, that's going to have the minimum value of -3. And then our function will cross the x-axis at 3 pi over 2. We'll move that out of the way a little bit. Then we'll have the maximum value of 2 pi and cross our x-axis again at 7 pi over 2. Move that one out of the way too. Now we can go ahead and connect these values as well. So we see our function will continue on in the same way, like that. So comparing this graph to our graph of sine, we see that vertical shift. Our min and max values are now 3 and -3. We've compressed horizontally, so our period was cut in half, so every other value had to be cut in half as well. And our graph is flipped since we had that negative value. So that would be how we use transformations in order to regraph a new version of a sine graph.